Hello everyone. Today's topic is Bayesian learning for machine learning. So in this topic we'll study the three parts. Part 1 is Bayes theorem, part 2 is Bayes network, and third one is naive Bayes algorithm. So before this you should know what is the probability and the definitions and what are the concept of the conditional probability and how the conditional probability applied in Bayes theorem. Now, what is the probability? Probability is a measure of the likelihood of an event to occur. Many events cannot be predicted with total certainty. We can predict only the chance of an event to occur, that is how likely they are to happen, using it. So there are so many definitions of probability, different authors given different definitions. Second one is probability denotes the possibility of the outcome of any random event. The meaning of this term is to check the extension to which any event is likely to happen. The probability is the measure of the likelihood of an event to happen. It measures the certainty of the event. The formula is probability is given by the probability of the event is equal to the cardinality of E by cardinality of S. And what is the cardinality of E? Or the number of events, favorable events or outcomes. The number of events favorable to an event E. And what is the cardinality of S? The total number of outcomes. Now what is the sample space? A sample space, generally denoted by S or U or E, is the set of all possible results or outcomes of a random experiment. Again, in the sample space there is a independent event. The independent event is when the probability of occurrence of one event has no impact on the probability of another event. Then both the events are termed as independent of each other. That is, probability of A, probability of B, they are totally independent. The probability of A intersection means there is no common element. So probability of A into probability of B. Then properties. The range of the probability is generally 0 to 1. The complementary event rule is the probability of A complement plus probability of A equal to 1. Same as our set theory. Rule of addition, probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. If they are mutually exclusive, then probability of A intersection B is 0. That is given in the disjoint event, that is your mutually exclusive events. There is no common things, and there is no common events, or they are not also independent to each other. If they are independent to each other, P intersection B can be written as PA into PB. So this can be, the addition rule will be changed if the both the independent events. Conditional probability, what we will study now, the probability of A given B is equal to probability of A intersection B by probability of B. Base formula is extension of the conditional probability. So probability of A given B is equal to probability of B given A into probability of A by probability of B. That is meaning that the B event already known, and you have to predict or find the probability of A. Now conditional probability. In the conditional probability, we have the two events A and B, and generally they may be independent, may be dependent, but we are considering here the dependent. And when the probability of A, we have to calculate the probability of A when the event B already known or happened, and this is denoted as A by B. That is, B already happened, A you have to calculate. So probability of A by B is equal to probability of A intersection B by probability of B. The condition is probability of B not equal to 0. In the reverse way, if the probability of B when the event A is already known, then it is the same as the formula probability of A intersection B by probability of A, where probability of A is not equal to 0. So conditional probability can be contrasted with unconditional probability. Unconditional probability refers to the likelihood that an event will take place irrespective of whether any other events have taken place or any other conditions are present. One of the objectives of calculating conditional probability is to determine whether two events are related or not. Now, conditional probability property, there are three properties are there. If E and F be events of the sample space S of an experiment, then we have probability of S given F is equal to probability of F given F is equal to 1. That is, if the same probability already F happened and you calculate the probability of the F, then it will be 1. Property 2, for the two probabilities A and B, or A and B are any two events of a sample space S, and F is an event of S, so that probability of F not equal to 0, then probability of A union B given F is equal to probability of A given F plus probability of B given F minus probability of A intersection B given F. Same as our the summation theory, but here we are considering the given probability F. Now for the complement case, if probability of A complement not equal to 0, then probability of A complement given B is equal to 1 minus probability of A given B. So only B is the change, otherwise the same as probability of A complement is equal to 1 minus probability of A. Dependent events, so A depends on B. So two events are dependent when the outcome of the event, first event influences the outcome of the second event. A event is deemed dependent if it provides information about another event. An event is deemed independent if it offers to information about other event, which provides the information about another event is called the deemed event, deemed dependent. And if there is no information about the other events, then it is called a deemed independent. If A and B are dependent events, then the probability of both occurring is probability of A intersection B is equal to probability of A into probability of B given A. Similarly, probability of A intersection B is equal to probability of B into probability of A given B. The example is that boarding a plane first and finding a good seat. Both are independent. We cannot say that you will get a good seat or not. Getting into a traffic accident is dependent upon driving or riding in a vehicle. So the traffic accident depends on the driving. If careless driving, accident will happen. Or you are in the riding a vehicle also sometimes traffic accidents happens. Independent events, if two events A and B are said to be independent if probability of A intersection B equal to probability of A into probability of B. Probability of A given B is equal to probability of A and probability of B given A is equal to probability of B. If both are independent, I am giving one example. Probability of, already we know that probability of A intersection B is equal to probability of A by B into probability of B. Now this is equal to probability of A into probability of B. So probability B cancels. So you get that probability of A given B is equal to probability of A. Similarly, you can go for the B by A case. So the example is taking an Uber ride and getting a free meal at your favorite restaurant. Both are independent to each other. You can make any one is the condition. Winning a card game and running out of the bread. We cannot say both are dependent. So the both are independent. So card game not depending on the running out of the bread. Growing the perfect tomato and owning a cat. Both are independent. Tomato is vegetable and owning a cat. It is your personal interest, hobby. Multiplicative rule. So in the multiplicative rule, the probability of A intersection B is equal to probability of B given A into PA, provides probability of A is greater than 0. If equal to 0, we cannot find anything. So it can be written as in the two ways already discussed earlier. And if both are independent, we can write probability of A intersection B equal to probability of A into probability of B. Now if both are independent, we have the probability of A 0.8 and probability of B 0.7. So this is equal to probability of A into probability of B. So it will be 0.8 into 0.7, 0.56. Now if A, B, C are three events, then the multiplicative rule is probability of A intersection B intersection C is equal to probability of A into probability of B given A into probability of C given A intersection B. That is, probability A is independent, probability B depends on the A, probability C depends on the A and B. So you can interchange any one thing, both result will be same. Suppose I write the probability of C into probability of C depends on the B and probability of B depends on the C and probability of A depends on the B intersection C. But you have to check that whether A, B, C they are depending to each other in which way. Similarly, for the four parameters, four events, the process is this one, probability of T, that is probability of T intersection I intersection G intersection P is probability of T into probability of I given T, probability of G, the third one, given T intersection E, and last one, probability of the P given T intersection I intersection G. If all the three events are independent from the first case, then you get probability of A intersection B intersection C is equal to probability of A into probability of B into probability of C. Now consider one example. In a group of 100 computer boards, 40 bought CPU, 30 purchase monitor, 20 purchase CPU and monitor. If a computer buyer choose at random and bought a computer bought a CPU, then what is the probability they also bought a monitor? You see that 30%, 20% purchase CPU and monitor. But you take randomly some buyer. Now in the first event 40 out of 100 CPU, so probability of A is 40%, that is 0.4. 20 buyers purchase both CPU and monitor. Now probability of A intersection B is 20% at 0.2. So probability of monitor is 0.3. Now you apply the conditional probability because our data is only these two is required. By the formula of conditional probability, probability of B given A is equal to probability of A intersection B into probability of A. So you are not using 30% monitor. You are using only CPU and monitor. So probability of B given A is equal to probability of A into B, probability of A intersection B, that is 0.2, and by probability of A, that is 0.4. So you get the 0.5. So it concludes that the probability that a buyer bought a monitor given that they purchase a CPU is 50%. If it is more than 50%, then you can say that it is sure, or there is a 50-50 chance. Second example, in a batch there are 80% C programmers, 40% Java and C programmers. What is the probability that a C programmer is also Java programmer? So let A is the event that a student is Java programmer, B is the event that student is C programmer. So probability of A given B is equal to probability of A intersection B by probability of B. So all data is available. So you will get the 40% Java and C is 80%. So 0.4 by 0.8, again you are getting 50% chance. Dependent and independent. How to find the dependent and independent? Method to identify independent events. Before applying probability formula, one need to identify an independent event. Few steps for the checking whether the probability belongs to dependent or independent event. Check if it is possible for the event to happen in any order. If yes, then go to step 2. Check if one event affects the outcome of the other event. If yes, then go to the fourth, that is dependent. Now, if no case for the first case, you cannot make any order, go to step 3. What is the step 3? Step 3 is it is independent. That is, we are finding that you cannot make any one related to each other. Then total probability. Total probability, suppose we divided into a sample space into k partitions, and every case the probability of B I is not equal to 0 for I is equal to 1 to k. Then for any event A of S, for any event inside the partition, probability of A is equal to probability of Bi intersection A, which is equal to probability of Bi into probability of A given Bi. So every case will verify for the B1, for the given B1 what is the probability of A, for the B2 what is the probability of A, and similarly for up to Bk. So you are getting this is the case, probability of A given Bi, because every probability case we know for individual partitions. Now in this diagram we have the A intersection B. So you are getting the 4 regions: A intersection B complement, A intersection B, B intersection A complement, A complement intersection B complement. Now if you find the A only, what is the probability of A? Because every case A is available, either A or A complement. So you get the probability of A is equal to probability of A intersection B complement plus probability of A intersection B plus probability of A intersection A complement intersection B plus probability of A complement intersection B complement. Now based on this, now go for the one example how the total probability is calculated. Now a group contains equal number of men and women. Of those, 20% of the men, 50% of the women are unemployed. If a person is selected at random from these 20% men and 50% women, what is the probability of the selected person being employed? So our question is unemployed, but you have to find whether he or she is employed or not. Suppose E is the event that probability the selected person being employed. So MN is selected, so probability is him being employed. That is, he will go to employed 20 by 100, but already it is unemployed. Similarly, a woman has selected, the probability for her being employed is 50 by 100. So what is the total probability? The total probability is probability of the man into probability of E by M, probability of W, that is a woman, into probability of E by W. So it is a 50%, so men both are same, so you take 50-50. So probability of man is 0.5, probability of woman is 0.5. So it is 1 by 2, 1 by 2. Probability man is 20 by 100 and probability of woman is 50 by 100. So you will get 7 by 20. What require is, it is based on the unemployed, but requirement is employed. So take the complement. So 1 minus probability of E is equal to 1 minus 0.35, which is equal to 0.65. So 65% people are employed, or a person is selected randomly, the person is employed. Now Bayes rule. In the Bayes rule we have the four concepts. One is the hypothesis. The events E1, E2, En are called the hypothesis. Prior probability. The probability of EI is called the prior probability of the hypothesis already known. Likelihood, you have to find some event A for which EI is already known, is called the likely to occur for the event A. Similarly, probability of EI given A, that is called the posterior probability. That is, you have to calculate the probability of EI already A is happen or A happened. So Bayes theory is called the formula for the probability of the causes. So what is the cause for this one? Since EIs are partition of the sample space S, one and only one of the event AI occurs in the calculation. That is, the one of the events AI must occur and the only one can occur. Hence the above formula gives us the probability of a particular EI, that is the cause, given that the event A has occurred. Already we know the concept. What is the meaning here? Suppose a patient has 3 symptoms and the result is fever. And out of the 3, some patients have the headache, some have body ache, and someone have the temperature, high temperature or some temperature measure. And the 3 events E1, E2, E3, that is 3 symptoms are there. And A is the cause. A is the result, that is fever. Now you have to calculate whether this fever is due to headache or body ache or due to the temperature or any combination. Now in this case, the probability of EI is the probability of the symptom probability of A given AI is the probability of the fever due to the symptom EI, and you have to check that what is the cause of the fever, whether it is EI or that is any one of the symptoms, and which has the highest probability, that is the symptom for the fever. Now you can see from this one, the diagram, the posterior belief, prior belief and evidence. So this is the evidence, that is the probability of B, generally marginalization, or sometimes called the evidence, because already B is the partition, or that is the result cause. Posterior belief is the highest probability, prior belief has the less probability, and evidence has the moderator probability between the posterior and the prior beliefs or the probabilities. So you can see here the Bayes theorem, probability of A given B posterior, the probability of A being true given B is true, and likelihood is the probability of B given A, the probability of B being true given A is true. Prior probabilities, the probability A being true, this is the knowledge, already you know, this is the fever suppose. Probability of B, marginalization, or it is the evidence for the particular fever. So if the multiple evidence are there, three evidence are there, three symptoms are there for the fever. Now total probability you can calculate using the, this is the conditional probability tree. So I have the two probabilities, probability of A and probability of A complement. From the probability of A, you will find the probability of B given A, that is the probability of A intersection B. Probability of A, again you can also calculate probability of B complement given A, that is probability of A intersection B complement. Similarly, for the probability of A complement, there are two cases, probability A complement intersection B and probability of A intersection B complement. So the sum of all the four is your total probability. Now what is the application? Already I told that every symptom we have to, there is a cause. Now if the events B1, B2, Bk constitute a partition of the sample space S such that probability of Bi not equal to 0 for I equal to 1 to k, and for any event A in S such that probability of A not equal to 0, then probability of Br given A is equal to probability of Br intersection A by summation of probability of Bi intersection k, which is equal to probability of Br into probability of A given Br by summation probability of Bi and into probability of B A given Bi. And this type of application is most important in many cases. For example, for the medicine, science, philosophy, engineering, sports, law, everywhere Bayesian interface is, inference rule is applied, and this is also called the statistical inference. And this total probability is generally used for the medical test, where you can find the what is the overall accuracy of the particular disease. Now consider the one example. The cat is allergy, that is it is allergy to someone, false positives and false negatives. Some person it is allergic, someone it is not allergic. Now for those we have two possibilities for A, so that pass or fail, yes or no. Hunter says she is itchy. There is a test for allergy to cats, but this test is not always right. For people, that is, she is saying that she is itchy. That is based on the allergy to the cat. But it is always not true, or maybe sometimes true. For people that really do have the allergy, the test says yes 80% of the time. And people that don't have the allergy, the test says yes. No allergy also showing yes, so 10% of the time. That is called the false positive. If 1% of the population have the allergy and hunter's test says yes, what are the chances that hunter really has the allergy? Now we want to know the chance of having allergy when the test says yes. Written as probability of allergy given S. Now go to the formula. Probability of allergy given S is equal to probability of allergy into probability of S given allergy by probability of S. Probability of allergy is probability of allergy is 1%. Probability of S given allergy, that is the probability of testing saying S for people with allergy, is 80%. The probability of S is probability of testing saying S to anyone. What is the percentage? So this is the important factor to calculate whether the cat has the allergy or not. Now go to the calculation. We don't know what the general chance of the test saying yes is, but we can calculate by adding up with those without the allergy. We are calculating total probability. 1% have the allergy and the test says yes to 80% of them. 99% don't have the allergy but the test says yes to 10% of them. So you see that there is a marginal gap. Let add that. Let us add that up. Probability of S is 1% into 80% plus 99% into 10%. So I am getting 10.7, which means that 10.7% of the population will get yes result. Now probability of allergy is S. So I am getting 1% into 80% by total probability 10.7. So I am getting 7.48%. So around 7% of the probability, that is 0.07 probability. Now what is the difference now you are getting? Previously already you know 10% of the time it is false positive. So it is coming under the, this is less than 10%. So you are getting that the same result because it is below the 10%. So I consider this is the result. So I am saying that this is false positive and false negatives. Now in fact we can write a special version of the base formula just for things like probability of A given B is equal to probability of A into probability of B by A plus probability not A, probability of B not A, B given not A. Now case study, the independent events. You lose a coin and it comes up head 3 times. What is the chance that the next toss will be a head? So you cannot say. The chance is simply half, 0.5, just like any toss of the coin. What is the deed with past will not affect the current toss. Some people think it is overdue for a tail, but really truly the next toss of the coin totally independent of any previous toss. Because already we don't know it is tail or head. It may head, maybe tail. Already you tossed 3 times. 3 times head got. Now next chance you cannot say it is head or tail because it not depends on the previous. The coin is totally independent. Now go to the graphical model, the Bayesian network. In the Bayes theorem, the graphical model is one of the important to identify the condition of the dependent and the independent, whether they are related to each other or they are not related to each other. Then what is the graph? Graphs are the intuitive way of representing and visualizing the relationship between many variables, like your family tree, electrical circuit, neural networks, or if then else conditions, and uh, the flow of the information. So all are represented generally graphically. So you can find what is the next information you have to follow or what is the previous information already available. So a graph allows us to abstract out of the conditional independence relationships between the variables from the detail of their parametric form. Now consider one example. Is A dependent on B given that we know the value of the C. So if you see the graph, you can say that whether B is depending on the A or depending on the C. It may be independent, may be dependent. That is A, B, C are related to each other. If they are not related, that is C is not related to A, C is related to B, B is related to A, then A depends on the B. We cannot say if B is not giving any information to A. But if A giving information to B, then B depends on A. You can get the reverse way. Graphical models allow us to define general message passing algorithm, what is in the operating system, that implement probabilistic inference efficiency. Thus, we can answer queries like what is probability of C is equal to C. That is, cause is already one of the, not all the causes, some particular cause, without enumerating all settings of all variables in the model. We are not considering others, or only considering for the headache. Suppose in the fever headache, if A is the fever and C is the condition is that your headache, then what is the probability that you will be you suffer in fever with the condition headache. So generally graphical model is the totally combination of statistics, graph theory and computer science. Why the computer science? We are going for the computation. Now consider this the three different graphs. The first one is A and B, both are independent, there is no relation. Second one AB, A implies B, B depends on A. So A's information required to the B. So here you can write this is the probability of A, B is equal to probability of B given A into probability of A. Second case, third case, you have the different way. What is the different? A depends on B depends on A and C also depends on A. So B and C depends on A. So here we can say that probability of ABC is equal to probability of B given A, probability of C given A into probability of A, because already probability of A is already known. Joint probability. Joint probability is the concept of combining multiple events or multiple variables to form the condition probability chain. So here suppose you have the n variables x1 to xn. then the probability of a different combination of x1, x2, xn are known as joint probability distribution. If probability of x1 to xn we written in the following way. So when I am going for the x1 to xn, so x1 depends on x2, xn. Now x1 is over into probability of x2, x3 up to xn. Second case, x1 is over, now go to the x2. So what is the probability of x2? Probability of x2 given x3 to xn into probability of x3 to xn. So in this way up to continue. The last one, probability of xn minus 1 depends on xn into probability of xn. So after probability of xn, nothing is there. This is the final value. And this is called the chain rule. And this is the process of another concept that is called the Markovian rule. In general, for each variable xi, we can write the equations as probability of xi given xi minus 1 to x1, which is equal to probability of xi given parents of xi. That is, what are the parents? Xi is the one of the element, so all are the parents of the xi. That is, xi depends on other variables. Then Bayesian belief network or Bayesian network. It is sometimes called the Bayes network, belief network, decision network. So it is a probabilistic graphical model that represents a set of variables and their conditional dependence by a directed acyclic graph. So this is a directed graph. There is no cycles are available because every one is not depending on others. Only there is a one-way cycle or one-way process is available. A Bayesian network is a compact, flexible, and interpretable representation of joint probability distribution. It is also an useful tool in knowledge discovery. That is, you can identify how they are depending in each other. As directed acyclic graph allow repeating causal relationship between the variables. So if you are going for the Bayesian belief network or Bayesian network, it specifies joint conditional probability distribution. They are also already told Bayes network, Bayesian network, belief network, and nowadays also they are telling it is probabilistic network. Then what is the use of this one? It allows class conditional independent to define between the subset of variables. What is the subsets are available? It will find the independence. It provides a graphical model of causal relationship in which learning can be performed. How the learning is moving from top to bottom. We can use a trained Bayesian network for the classification. So if already a network is trained based on the calculation, based on the model that we are using the number of variables, defining the formula and calculating, then the same model can be used for the classification for other data. There are two components defined in Bayesian belief network. One is the directed acyclic graph DAG, second was the set of conditional probabilistic table. So directed graph is a graph where each node is directed acyclic graph represents a random variable. That variable may be discrete or continuous values. So the each node may be a discrete or continuous value. These variables may correspond to the actual attribute given in the data. Bayesian network is a directed acyclic graph in which each edge corresponding to a conditional dependency. So edge is showing that it is dependence, and each node corresponding unique random variable. Formally, if an edge AB exists in the graph connecting random variables A and B, it means that probability of B given A. Edge is from A to B. So in effect, edge is a factor in the joint probability distribution. So we must write probability of B given A for all values of B and A in order to conduct inference. So already you know that this is the A and this is the B. So B depends on A. So we write probability of B given A. Now formal definition. A Bayesian network is a directed graph. G is equal to vertex and edges, B, the set of vertex and edges, together with a random variable xi for each node I is equal to B, one conditional probability distribution CPD, probability of xi given xai for node, specifying the probability of xi conditions on its parent's value. Thus, a Bayesian network defines a probability distribution. Conversely, we say that a probability distribution PP. Conversely, we say that a probability PP factorized over a DAG, G if it can be decomposed into a product of factors as specified by G. Then Bayesian networks satisfy the local Markov property. We state that node is conditionally independent of its non-dissident given its parents. That is, every node is independent if it is not related with parents. This property allows us to simplify the joint distribution obtained in the previous section using the chain rule or to a smaller form. After simplification, the joint distribution for a Bayesian network is equal to the product of P probability of node given parents of the node for all nodes stated below. So this is the simplified product formula. Probability of x1 to xn is equal to pi from I equal to 1 to n, probability of xi given x1 to xi minus 1. If this is the 1, then we get the 1. So x1 given x1 already 1. Then if x1 xi is 2, you get the x2 x1 and next one is 1, only 1. Now when you are going to the 3, probability of x3 x1 to x2. So in this way find that every one is depends on the previous node. So probability of xi given parents of xi. In the larger network, the property allows to greatly reduce the amount of required computation, since most nodes will have few parents relative to the overall size of the networks. So every node is not depends each other. Only some of the nodes may have the very less parents or less number of inputs. To work out a value for the probability of a, B, then we would need a distribution table of PA, one for the probability of B given A. The nodes are separated into those where we can see their values directly, that is called observed nodes, and hidden or latent nodes whose values we have to infer and which not have a clear meaning in all cases. So some observed values are there and some are hidden or latent nodes are there. Then what is the inference? Inference is finding some conclusion using some rules. So there are two kinds of inferences depending on whether the observations that are made come from the top of the graph or the bottom. So it may be coming from the top or bottom, depends on the type of information. If we have a set of observations that can use a predict an unknown outcome, then we are doing top-down inference or prediction. If outcome is known but the causes are hidden, then we are doing bottom-up inference or diagnosis. So one is the prediction, second one is the diagnosis. And so this is the example of, suppose you don't know whether you have the malaria fever or jaundice or anything, then what you are doing? You are testing all the parameters, all the symptoms and the parameters and identifying it is a malaria or the jaundice. Now suppose this is called the prediction, unknown outcome. We don't know what is the outcome. It may be jaundice or malaria. Now you are sure that you are the malaria, and what is the cause? The doctor identified you may have the malaria. So they diagnose or take all of the parameters, all the symptoms, and also test different components of your body or urine, anything, what are the components are required. Then they confirm that that is you have the malaria or you may not have the malaria. That is your diagnosis. Either way, you are working out the value of the hidden unknown nodes given information about the observed nodes. Some are hidden, some are already observed. The graphical model is that we can read the conditional probability from the graph. If there is no direct link, then variables are conditionally independent. Given node that is already included, so those variables are not needed. If there is no direct link is given, that is not directed, any direction not given, then it is independent. They are independent to each other. Now here arrow marks are given. So R depends on B, A depends on B, and S depends on R, and S depends on A. Now consider this example. For this example, you start by predicting whether or not you will be scared before the examination. So you have the different cases are there. S is the scared about the information. A is the attending the lecture. R is you revise the course or not. B is whether the exam was boring. If the exam is boring, then you are not reading. A is you are not attending the class and you are scared about the examination or before the examination. So there are S, R, B, A. Four parameters are there. So probability of the B is 50-50. The subject is bored or may not be bored. Then you are getting the other case. Depends from the B. You are not reading. You are reading true 0.3, 30% are reading, 70% are not reading. And false case 20%, and you know but you are not reading. Then attending, regular attendance 10%, absent 90%, or false, this is a true, this is a false. So false, absent 50%, and false not absent 50%. That is attending the class, not attending the class. Then RA. Now both are S depends on RA. So probability of A, probability of S, and probability of not S. Probability of S is both are true, 0, 1. R is true, A is false, 0.8, 0.2. R is false, A is true, 0.6, 0.4. Both are false, probability of S is 1, probability of negative S is 0. So both are true means you are not scared about the examination. So you can appear the exam. So you can find the probability of B, R, S where the lowercase letter indicate particular value that are uppercase variables are taken. So probability of B, R, S can be calculated using the summation of B into probability of B into summation of RA, probability of R given B into probability of A given B into probability of S given R and A. So this is totally independent and this is dependent. That is probability of B is totally here. Probability of R is also here. So if I know both whether or not you attended lectures and whether or not you revised, then I don't need to know if the course was boring, since there is no direct connection between B and S. That is last point to B. S to B there is no connection. Suppose that you did not attend lectures but did revise. In that case, the probability of you being scared can be read of the final distribution is 0.8. So I am getting the 0.8 here. I am going for the positive result, not negative. The power of the graphical model is when you don't have full information, it is possible to marginalize over any of these variables by summing of the values. Suppose that we know that course was boring and want to work out how likely is it that you will be scared from the exam. So going for the score, it is boring 0.5. Then probability of S is equal to probability of R given B into probability of A given B into probability of not S given RA plus probability of RB into probability of negation of A given B into probability of S by R S given RA plus probability of not R given B into probability of A given B into probability of S by R S given probability of S given RA plus probability of not R given B into probability of not A given B into probability of S given RA. So after the getting all the values from the table, we get 0.38. So it is coming under 0.4 of the category S, so that you will not scared before the examination. So 0.4 is coming here. So you are not scared before the examination. So similarly, you can go for the other example. There are three cases are there. You can construct a Bayesian network. Harry installed a new burglar alarm at his home to detect burglary. The alarm reliably responds at detecting a burglary but also responds for minor earthquakes. Harry has two neighbors, David and Sophia, who have taken a responsibility to inform Harry at work when they hear the alarm. David is going outside, he is working outside. David always calls Harry when he hears the alarm, but sometimes he got confused with the phone ringing and calls that time too. So if the both are ringing and call both are happening, then he is not able to identify. On the other hand, Sophia likes to listen to high music, so sometimes she misses to hear the alarm. Here we would like to compute the probability of burglary alarm. What is the problem now? Calculate the probability that alarm sounded, but there is neither a burglary nor an earthquake occurred. And David and Sophia both called the hurry. So you have to construct the conditional probability table CPT to find the relations. So events are burglary B, earthquake E, alarm A, David calls D, and Sophia calls S. Now from this you can find that the true is 0.002, false is 0.998, burglary. Earthquake is 0.001 and false is 0.999. Alarm will be get effect from the B and E. So true 0.94, true false 0.95, all the true cases, false 0.69, false 0.999. D depends on the alarm, David calls 0.91 true, false 0.05. Sophia 0.75 true, false 0.02. Now we can write this probability in this form. Probability of D, S, A, B, E. That you are going for calculating total probability. So probability of D given S, A, B, E, probability of S, A, B, E, probability of D given S, A, B into probability of S given A, B, E into probability of A, B, E. Again now simplify. In this way you get the final result. Probability of D given A, probability of S given A, probability of A given B, probability of B given E, and probability of E. Because some are not available for the particular case. They are not directly related. Now, probability of B true is 0.2, probability of B false is 0.998. Probability of E is true 0.001, false is 0.999. Then conditional probability are the three tables, and these three tables, one is for the alarm, true, true 0.94, 0.406 and 0.001 and 0.999 for the alarm. The conditional probability of alarm A depends on the burglar and earthquake. Conditional probability table of the David calls. The David that he will call depends on the probability of the alarm. Similarly, Sophia calls depend on the parent node alarm. So 0.91 true for the David and false 0.05. For Sophia, true, S is true, true is 0.75, false is 0.2. Now I will calculate the total statement. From the formula of joint distribution, we can write the problem statement in the form of probability distribution, probability of SDA, negation of B, negation of P, because both are false and they given the true result. Probability of S given A into probability of D given A into probability of A given negation of B and negation of E, and into probability of negation of B into probability of negation of A. Finally, you get 0.007, 0007. So David and Sophia both called the Harry, as the probability come under the 0.02 for Sophia and 0.5 for David. Hence, Bayesian network can answer any query about the domain by using joint distribution. So this is the end of the Bayesian network. Next section we discuss the Bayesian classification. Have a good day.